Hi everyone, this is your decidedly not artificial intelligence virtual physical chemistry instructor, Dr. Hopkins, and I'm here showing you the second of our videos on the hydrogen atom. And we're still sticking with our quantized electronic motion. All right, so what we're going to do at this point is look at the angular momentum of a hydrogen atom. So we're revisiting the spherical harmonics and the rotational motion we discussed when we talked about the rigid rotor, but now in the context of atomic structure. And so we have our wave function we had from the last video. It's an eigenfunction of both of our angular momentum operators, both the total angular momentum, the L squared, and the Lz. And out of those, we get our two quantum numbers, the L, which is our total angular momentum, or our orbital angular momentum quantum number, and m sub L, which is our specifies the direction of the orbital angular momentum. So one specifies how fast it's rotating or revolving around the nucleus, and the other one specifies the direction. All right. And then what's not included in this angular momentum, just to complete the three quantum numbers, so n is what we call the principal quantum number. Of course, it specifies the energy. All right, so if we look at these quantum numbers, the first, so every energy state or every eigenvalue is dependent upon only n. So we have the first energy level, the n equals 1, and then based on the rules for assigning the other two quantum numbers, we have a state that is described as 1, 0, 0, so n, l, m sub l. The degeneracy is 1. That's what we would commonly call the 1s orbital, correct? And so if we go to like state 2, so n equals 2, here we have fourfold degeneracy because in the hydrogen atom, the 2s orbital and the 2p orbitals are the same because they have the same n quantum number, and so forth. So you go on to 3 and whatnot. And so each one of these states, in terms of the quantum numbers, describes the quantized energy and spatial distribution of the electron orbital, the electron orbiting around the nucleus in a hydrogen atom. All right, so here are some of the wave functions. I'm not going to show them, but you'll notice, or I'm not going to talk too much about them, but I've written out the first three. Your textbook on page 212 and 213 includes the complete wave functions for, I think, at least up to the d orbitals, the 3d orbitals, excuse me. So we have the 1s orbital, and you can see there's no angular dependence. The 2s orbital, once again, no angular dependence that dictates their shape. Now we go into, and I just show one of the 2p orbitals and have a cosine theta. Now we have an angular term. So we now have a shape to our particular orbital. And what that ends up being, so the s orbitals, as I said, have no angular dependence. And the shape, now remember, when we're looking at something that is an observable, we're always looking at the psi star psi, or the absolute value of the psi squared. And I just have written it as absolute value of psi squared. We're looking at the probability. So the probability is what gives us the shape of an s orbital. And here I've just plucked something out of ChemDraw that shows the s orbital shaded. P orbitals have an angular dependence, and typically you'll have a couple of lobes. We have a node, so we'll have a region where there's no probability, angular probability to be in the center of this. And then d orbitals have two different shapes. I think I showed in class when we were talking about the rigid rotor kind of what a torus looks like, the actual solutions. If we map them out, one of the p orbitals does look like a torus. And so if we look at these in terms of what we're commonly used to, so what you used in inorganic chemistry, what you used in general chemistry, you use the Cartesian base, px, py, pz, dxy, dyz, etc. All of those are linear combinations of the eigenfunctions that are the solutions of the Hamiltonian shown on 212 and 213. So if we actually go through and solve the Hamiltonian, we get the answers on page 212 and 213, but we most commonly refer to orbitals as the real wave functions that are shown on page 216 in your book. So if you look them, I'm not going to write them out. You can look them up in the book. These real wave functions are eigenfunctions, the Hamiltonian and the total angular momentum operator, but they are not eigenfunctions of the the LZ. So they do not return the actual the direction um, of that operator. Now, the reason why we don't just use the imaginary wave functions, imaginary actual solutions, is that as we use hydrogenic wave functions in larger atoms with more electrons and molecules, they kind of apply some intuition. It's a lot easier to think in X, Y, and Z rather than in the imaginary plane and so forth. And so they build some chemical intuition. The next video that we're going to go through, we'll talk a little bit about radial functions of the hydrogen atom. And you'll notice I'm trying to keep these videos I'm trying to keep them as close to 5 minutes as possible so that they are not, don't go on and on and on and nobody's listening to them at the end. So until next time.